In the previous episode, we went over support vector machines for linearly separable data and went through some of the maths behind them. In this episode, we're going to focus on support vector machines for non-linearly separable data. So here we have some non-linearly separable data. That is, we can't really draw a straight line that separates the classes in our data. For this, we may want to calculate a nonlinear support vector machine, but this may overfit our data. We may prefer to have a linear support vector machine that makes some misclassifications. In this example, here, here, and here. Ideally, we would want all data points of class A on one side of the hyperplane and of class B on the other side. So this is what is called a soft margin support vector machine. That is, we allow our support vector machine to make some misclassifications. In order to allow this, we have to make an adjustment to the objective function. Remember in the previous episode, in order to calculate the hyperplane with the largest margin, we were minimizing 1/2 times the norm of the vector of weights of the hyperplane squared. Now with a soft margin support vector machine, we're adding this extra part here. C is given as the regularization parameter, and psi as a slack variable. Let's take a look at these 4 points here, x1, x2, x3, and x4. Psi is given as the distance between the data point and the class's margin. x1, x2, and x3 all belong to class A, and class A's margin is given here, and x4 belongs to class B, and class B's margin is given here. With a soft margin support vector machine, we allow points to lie within the margin, so for example x1, and we also allow points to lie on the side of the other class. So for example, the point x4 belongs in class B, yet is on the side of class A. In the previous episode, we said that the equation of the hyperplane is given as W transposed x plus B equals 0. We also said that the equations of the margins are given as W transpose x plus B equals 1 and W transpose x plus B equals -1. Ideally, we would want all data points xi that lie on class A side to follow the following inequality. That is, W transpose xi plus B is bigger than or equal to 1 to indicate that the data point belongs in class A. And ideally, for all data points xi that lie on class B side, which is this side, to follow the following inequality. That is, W transpose xi plus B is less than or equal to -1. With a soft margin support vector machine, we allow data points, so for example x1, to lie within the margin. We also allow points, like x4, to lie on the wrong side. To allow this, we have to make an adjustment to these two inequalities here. For all points that lie on class A side, we reduce the boundary by a value of psi, and so W transpose xi plus B becomes bigger than or equal to 1 minus psi. We also reduce the restriction for the points on class B side by, instead of saying W transpose xi plus B is less than or equal to -1, we say less than or equal to -1 plus psi. These inequalities are reflected in the conditions of the objective function here. For yi equals to 1, that is, the data point belongs to class A, we obtain W transpose xi plus B is bigger than or equal to 1 minus psi, and for yi equals to -1, we can multiply both sides by -1 to obtain W transpose xi plus B is less than or equal to -1 plus psi, which were the two inequalities shown in the other slide. We also need to ensure that the value of each of our slack variables are bigger than or equal to 0, and this is for I equals 1 to m, and m is the number of training examples. What if our data is better separated by a nonlinear function? For example, a polynomial function shown here. To produce a nonlinear support vector machine, we make use of what is called a kernel function. Depending on the kernel used, the kernel function transforms our data to a feature space where the data becomes more likely to be linearly separable. This is known as the kernel trick. To illustrate how this works, take a look at the following one-dimensional data. Here we cannot separate class A and class B with a single straight line. Using a polynomial kernel, we can project the data to a two-dimensional space where we square each point. So now we have this new axis here, x1 squared. We can see now that the data has become linearly separable. So here we made use of a polynomial kernel, and this is commonly used when the data can be separated by a polynomial function. Again, the process of transforming our data to a higher dimensional space, where it then becomes linearly separable, is called the kernel trick. Before going on to look at the different kernels which we use to transform our data to become linearly separable, we're just going to look at what's called the dot product. So let's say, for example, we had two data points, x1 and x2, and x1 took the values of 127 and x2 324. The dot product is calculated with the following. So we do 1 times 3, 2 times 2, and 7 times 4, which gives us 35. This dot product is used in kernels in order to transform our data to higher dimensional spaces. So for example, for linearly separable data, we can make use of what's called the linear kernel, where we simply just take the dot product of each of our features, and this is done to speed up the calculation of the support vector machine classifier. For data that can be separated by a polynomial function, we can make use of the polynomial kernel, and this has a kernel coefficient gamma, independent term r, and degree d. We applied this kernel to the example earlier with gamma equals to 1, r is equal to 0, and d is equal to 0. So applying this kernel with the following conditions, we would get 1 times x1 plus 0 all squared, which is just the same as x1 squared. So we would be creating a new column with each observation squared. And lastly, we have the Gaussian radial basis function, or RBF, and this kernel works for many cases and is used when there is no prior knowledge about the data. So for this kernel, we do e to the power of minus gamma times the Euclidean distance of xi minus xj squared. And this is for gamma bigger than 0. So in summary, we can separate non-linearly separable data without overfitting using a soft margin support vector machine. So for this, we introduce the slack term xi to the objective function. To produce nonlinear support vector machines, we can make use of the kernel function, which maps our data to a feature space where it becomes more likely to be linearly separable. So for example, we mapped the data of x1 to x1 squared. And lastly, we looked at the Gaussian radial basis function kernel, which works for many cases and is used when there is no prior knowledge about the data. So in the next episode, I hope to be implementing support vector machines for non-linearly separable data, where I hope to make use of this kernel. Thank you guys very much for watching, and I hope to see you guys in the next episode.